So we're going to continue from last time where we defined what a vector space was, which I'm not going to write down the definition again. It's like 10 things. But we started looking at some examples. But let's review some things we need for vector space.
Jhevon?
Yeah?
I don't know if it relates to this, but you emailed us saying that you want us to remind you about Cramer's rule or
Oh, yeah.
Cramer.
Oh, geez, thanks. Fully someone read the email. Okay. So Cramer's rule, because this is on the test. It was something that I meant to do, but I forgot. So let's stop off there first. And we actually showed this with the 2x2 system when I was talking about where the determinant came up. And I showed you in a 2x2 system when I tried to solve for x and y, the determinant that we know about from the 2x2 case showed up in the denominator of the solution. It turns out that something like this is true in general, so I just wanted to make sure we looked at that before I continue with vector spaces. Because I am going to ask you to use it on the test. So it's just kind of basically a formula you should know how to use, when to use it. When it will work, and when it does work, the results will be. So here's the idea. Let A x equals B. By n system equations. Let D equals the determinant of the coefficient matrix A. Let DI equals let me make this a little bit more suggestive. Determinant of AI. So I want you to realize that this is relating to the coefficient matrix always. By replacing, now I'll show you an example of this if you need to. Replacing the ith column of A with B. Then we have three cases. One, if your D is not equal to 0, then the system has a unique solution. Given by xi is equal to di divided by d. This is where I'm thinking of the vector x as just a bunch of components, x1, x2, x3, all the way down to xn. So xi can represent any number, so it can be x1, x2, x3, x4, whichever one I want to solve for. And what I can do is I'm going to find the determinant of the matrix that when I replace that column with the matrix B, I'm going to find the determinant of that, I'm going to divide it by the determinant of the coefficient matrix. Turns out that will give you the solution for each variable in the system, as long as the determinant is non-zero, so you can divide that. We'll do an example. That's one case. Second case is, if D equals 0, and all the di are also 0, then the system has infinitely many solutions. So if you can verify that this guy is equal to 0, which you can just compute, and also it is also the case that every single one of these guys are equal to 0, you would have infinitely many solutions there. You won't have a unique solution. The third case is that if d equals 0 and any of the di is not 0, then the system is inconsistent. Right? And we know that there are really only, this covers all three cases for the possibilities of solutions to a system. You can have a unique solution, and this is when you'll know you'll have it for a square system. You can have infinitely many solutions, and this is when you know when you're in that situation. Or you can have no solution, and this is how you know when you're in that situation. Notice these two, they never really tell you, especially particularly this one, it doesn't tell you what the form of what the solution looks like. You have to obtain that by other means. But in the event that you have a unique solution, we actually know exactly how to find all the variables. It will be found using that formula. Okay? So let's actually do an example here where you can see how the notation is applied. So we find the determinant of A, and then for each variable, we're going to want to replace that column of A with B. And if I take the ratio of the determinants, we'll get the answer. So are we done copying this down? Okay. Let's do an example. Let's do one that we know the answer for already, so we can verify. One of the first 3x3 systems we did that we knew had a solution. It went this far back. Okay, here we go. So this will also give us more practice on finding determinants as well as applying Cramer's rule. Minus 2x1 plus x2 minus x3. What was I copying this one? Let's equal to 4. x1 plus 2x2 plus 3x3 equals 13, and 3x1 plus x3 equals minus 1. Okay. Yeah, so we actually did this before. We know what the answers are. It turns out that our x was minus 1, 4, 2. Okay, so we know what the answer should be. So let's actually just verify that Cramer's rule works here. So Cramer's rule should give us that there's a unique solution. And you can verify the other parts with the other two. I gave an example that was inconsistent and an example that had infinitely many solutions. You can do something similar to this and show that these things actually happened in that case. So let's say I don't want to find everyone at the same time, but I want to find one particular guy. So I can say something like use Cramer's rule to solve for x2. So here's how it's going to look. First of all, note, what is the A here?
Your original matrix.
Yeah, so what is that?
2, 1, negative 1.
Minus 2, 1, negative 1.
1, 2, 3. 3, 0, 1.
Okay, so let's actually find the determinant of A. How'd you do that?
So 2 times, negative 2 times 1 minus -1 is 3. Plus. Right?
Wait, where are we going here?
I was doing a column expansion.
Can we?
Yeah, but tell me where you're expanding.
Which row?
Oh, sorry, I was expanding in the middle row. Sorry, middle column, because there's a 0 there.
Okay.
So 2 times -2 times 1,
So you're expanding here,
right?
which means you have to do a plus sign, minus sign. We could do a pivotal condensation here, but whatever, let's actually go with brute force it. So that's a plus sign, minus sign, this would be a plus sign. So it ends up being -1 times, block out everyone in his or in his column. It's 1, 3, 3, 1. Plus 2 times, block out everyone in that row in that column. -2, -1, and 3, 1. Right? So this is going to be, this is 1 minus 9, right? So that's minus 8 times -1, that's plus 8. This would be -2 plus 3, this is 1, so this should be 10, right? Everyone agree there? So now, what I care about is finding D2. Now this is just the determinant of A2, and my A2 is the determinant of the second column, which is this guy, is going to be replaced by the B column, right? So the variable that we care about to solve for, we're going to replace the column that has to do with that variable with the constant column. So here we would have 4, 13. I probably should replace the other one so we could keep that 0, but let's go. -2, 1, 3, -1, 3, 1. Okay, so now we're going to find the determinant of this guy. Let's do some reduction here. I'm going to replace row 1 by adding row 1 and 3. So that's a type 3 operation. That's not going to change the answer. 1, 3, 0. And I can do another one. Let's see that. Okay, so where do we want to expand along? First row, first column is kind of the same. So this is a plus, minus. So this is going to be equal to plus 1 times, block out everyone in that row in that column, 13, 3, -1, 1. -3 times, block out everyone in that row in that column. It's 1, 3, 3, 1. This will give us 13 plus 3, that's 16, minus 1, minus 9, it's minus 8, times -3, it's what, 24? Right?
Yes.
And that would give us what here?
40.
That would give us 40. So this would mean that my x2 is equal to d2 over d by Cramer's rule, which is going to be equal to, I just found this determinant, that's 40. I found the d earlier, that's 10. And so the answer should be 4, which we... So that's just Cramer's rule. We can actually solve for any variable. Not even, the power of this rule is that it allows you to pick and choose who you want to solve for. You don't have to solve the entire system all at once. Sometimes you might only care about one particular guy. And if you're in the event that you have a square system, you can actually use determinants to help you find this one particular guy. So there'll be a problem like that in in the test where I'm going to say, here's a system, solve it using Cramer's rule, and this is what you would do. So I'll tell you which variable I care about, which one I want you to solve for, and you have to figure out what two determinants to find to get to the answer. So it's just applying determinants to solving systems. This is another useful place that determinants show up. So as long as the determinant of your coefficient matrix is not 0, which in this case is not 0, this means a unique solution by Cramer's rule, right? If that's 0, then there is no unique solution. You either have no solution or infinitely many, and the way you can know you have no solution is if one of the other determinants is not 0. If all the other determinants are also 0, you have infinitely many solutions. And you can try that with the other examples I gave you when we did this on that day. So the example where I gave you that it has infinitely many solutions, you can verify that the determinant is 0 and at the same time d1, d2, and d3 are 0. And the system I gave you that had no solution, you can verify that the determinant of the coefficient matrix was 0 and one of either d1, d2, or d3 was not 0. Right, so that's Cramer's rule. Right, so rule in terms of determinants that talk about solutions to square systems. Are there any questions on that?
So for when you're finding the determinant on D2, you just swapped out column 2 with 413 and
You mean what I was doing here?
Yeah.
I added row 1 to row 3,
Okay.
which is a type 3 operation. I could have gone further, but two 2x2s we can do. Any other questions on? Yeah.
So in the case the determinant A is 0, you can't use Cramer's rule, right? Or to find
Well,
the other-
you can use it to say whether you have infinite solutions or no
only
solution.
one of those two, right?
You can
Okay.
use it to conclude that. But remember, in the case that we have infinite solutions, there is actually a way to write down what those solutions will look like in terms of parameters, right? But Cramer's rule is not going to help you there. Cramer's rule will just tell you, you're in this situation, now you're on your own, right? But in the case that you have a unique solution, Cramer's rule will tell you exactly what the answers are. Right. So in the unique solution case, it'll tell you what the answers are. That's the formula. Find these two determinants and take the ratio. But in the other two situations, it will identify them for you, but it won't help you otherwise. Like it won't tell you which one of the equations messed up or how to write it in terms of parameters. But yeah. So that's going to be a problem. And some of you may have seen this before. Maybe in algebra class you guys did it with 2x2s or something like that. Maybe. I know in the old version of Math 190 here, college algebra, they used to do 2x2s. Cramer's rule for 2x2s. Now let's go back to chapter 4. Vector spaces. Called. Tell me what makes up a vector space. How do you know when you have one? You're looking at one. What are the things you need to verify? What are the things you need to check? What are the things you need?
That you have a field.
You need a field. One, you need a field. Right? This is where your scalars come from. Scalars live here. Right? This will be R or C or S. Right? But there are other fields out there, but we'll mostly use R and C in this class. So you need a field. That's where you're going to get your scalars from. Your constants come from a set, which is called a field, which I told you there's a strict definition for this, but for our purposes, it's just some set that behaves like the real numbers under addition and multiplication. And that's, remember, addition and multiplication is in quotations. It could be defined in some arbitrary way. of combining elements. What's the next thing you need?
What you said?
Huh?
You need addition and multiplication, some sort of definition, and another set. And
On what? Another set. You need a non-empty set. You need a non-empty set, call it V, and your vectors live here. These are just the elements of this set. Okay. What else do you need? So I have a field, which is a set that behaves like the real numbers under two operations that combine elements. I have some non-empty set, the elements of which I call vectors. What else do I need?
you need the definition of those two operations.
I need two operations on V. Which we would call addition and scalar multiplication. How do you describe addition? Tell me how you would think of it. Think of addition.
You take two elements.
Right? A rule, and of course the rule would depend on context, whatever would make sense to you in context, to take two vectors and create another vector. So an addition operation is just going to be a function that takes two vectors of your set as inputs. It will output one vector of the same set as the output. Any rule that achieves this is called an addition rule. What is a scalar multiplication?
You take an element of your field, combine it with a vector, and get a vector.
Right. So it's a rule that combines things from two different sets. So it's a function that takes inputs from two different places. Right? The addition rule takes both inputs from the same place. The scalar multiplication rule will take an element from each one of these sets and combine them. So this is a rule to combine a scalar that is an element of your field and a vector that's an element of the set that you have to create another vector. What's the fourth thing you need? All right, so you have your field, you have a set, you created two operations on this set that does these things. What is the fourth thing you need? Now the fourth thing is a big thing. The fourth thing is pretty much the definition. The rules need to obey the 10 axioms of the vector space, right? So it's not like you can come whatever rules you want. No, the rules as defined, it must obey the 10 properties that we listed. The operations on V must obey the 10 vector space axioms. Now, if one of the things that you set up in steps 1 through 3 causes something down here not to work, it's not a vector space. And we looked at several examples last time. We're going to look at a couple more, and then we'll talk about subspaces and how to identify those. And most of today is going to be about me giving you some examples of these objects, right? But we're not really going to be playing around with them too much at this point. We'll prove a fact or two here or there, but most of today is about examples. How do you know when you're looking at one of these guys? Now, it's important also for you to know is that a vector space, when all these are fulfilled, we say V is a vector space. The word they normally use is over. So let me call the field here F. So V is a vector space over F with respect to these operations. Right, so a vector space isn't just one thing. There are many things that have to kind of come together, right? It's not just a set, it's the set equipped with rules that plays with another set, which we call the field, and they have to play together in 10 specific ways. I know that's a lot, but that's what definitions are now. Right? Which, from now on in advanced mathematics, you're going to realize that definitions will always have this flavor. You never really define something anymore by what it is. You will define something by what it does. Right? That's going to be a very big difference between elementary math and higher mathematics. Right? Your definitions are always going to tell you, oh, we need this to do something. Right? You can't just exist on your own. What can you do? Right? You can't just show up. You got to be useful, right? So it's good. It's not just the set by itself. The set plays with another set. It's equipped with operations that perform these 10 things. You need to be able to do these 10 things, or you're not a vector space. Okay. So that's one thing. And people don't normally give this warning, but I'll give you this warning. A vector space is not a field. Don't take things for granted. Right? So there are times when I'm going to be proving things to you that might seem obvious. You know, like, why do we have to prove that? Isn't that obviously true? No. Usually when that happens, it's obviously true for a field, but we're not working with a field anymore. Okay? So a field has more structure on it. A field can do more things. A field will have an operation called, not scalar multiplication, it will be called multiplication. And that is a rule that can define between two vectors. It'll be very similar to an addition rule, which from arithmetic you kind of already know, right? Addition and multiplication have a link together. You ever notice it, like in arithmetic? Multiplication is kind of like repeated addition. When you say 2 times 3, you're really adding 3 over and over at the same time. They're very similar. The difference is whenever you can't always take a multiplicative inverse, right? Whereas addition, the inverses you almost kind of get for free the way it's normally defined, but reversing a multiplication rule, that is division, is kind of a luxury, right? So that doesn't always happen. And in a field, you get that luxury for all non-zero elements. So a multiplication rule is kind of like an addition rule, except it's invertible for all non-zero elements. Okay, so that's the kicker, right? And fields have that extra operation. So there are a lot of things that will work out very nice and they'll seem familiar when you're working with fields. In vector space, this is not true, right? We don't have division. We don't even have a multiplication rule. There is no rule in a vector space that multiplies 2 vectors. You would have known that. There's no dot product or cross product as far as vector fields are concerned. It's not a thing that is a concern. Right? We only care about how these 2 operations behave. Right? So you'll see a lot of things that will seem obvious to you, but that's because you're thinking of things in terms of the real numbers. The real numbers are a field. They're not a vector space. They will be able to do more things. And so there are things that I'll be proving that we can do here that would seem obvious, but it's not obvious at all because a vector space can't do all the things that a real number can do. And so you need to be aware of when familiar properties will work out from when they won't. Okay? We looked at some examples. There are tons, especially in mathematics. So I gave you the examples about R. Basically Rn over R, right? So that's like a bunch of examples. What other examples did I give you so far? I don't remember. We looked at symmetric matrices were an example, right? where our addition and scale multiplication rule is matrix addition and scale multiplication. Look at a non-example. And by n invertible matrices, we're a non-example. These do not form a vector space. Right? Why? Because you can add two invertible matrices and not get an invertible matrices, right? So if A is a invertible matrix, turns out that the negative of A is an invertible matrix. And if you add A and negative A, you get the zero matrix, and the zero matrix is not invertible. You can't reverse the rule determined by the zero matrix because it kills all your information. You won't know who came from what. Other examples.
C over R.
C over R is also an example. C over C is an example with the usual arithmetic.
Z over
Here.
Z,
Come again?
Z over Z.
Z over Z is a non-example. Why?
Because Z is not a field.
Z is not a field. Here's another one. Again, using the usual arithmetic, meaning what we know from elementary mathematics, set of continuous functions form a vector field. You know, it's a set of continuous functions. If I look at the set of all possible continuous functions, they will, under these operations, where my scalars are coming from the real numbers. So I can look at the set of all continuous functions. We call these C, minus infinity, infinity. This is the notation for continuous functions on the real line. Continuous functions on R, which is sometimes called negative, the interval negative infinity to infinity. Right? You can go through with the vector space axioms and it will work for all of them. Right? You add two continuous functions, it's a continuous function. Right? You can add them in any order. The zero function is the zero L vector for the continuous functions, and you can go down the list and you'll realize that if you can combine continuous functions in those 10 ways and they'll all work out. You can have things like C1, C2, Cn on minus infinity to infinity. There is even a guy who calls C infinity, from minus infinity to infinity. And these are elements you'll play around a lot more with when you get to like advanced calculus and real analysis and things like that. This is the one-time differentiable continuous functions. And this is the two times differentiable continuous functions. And this means you can differentiate it n times differentiable continuous functions. This guy means an infinitely differentiable continuous functions. By the way, these are the guys that we can form Taylor series for. The other guys we can't. Right? So back in Calc 3 when you were looking for forming Taylor series, that you want to approximate some continuous function with a polynomial, these are the guys where that work. The other guys can't. If you can only differentiate a finite number of times, you can't create a Taylor series. By the way, here's an example of a C1 function. That is not C2. So that's it. Make sure. Yeah, that's an example of a function. Because I kind of want you to realize, because especially when you're doing calculus, a lot of the functions you play around with live here. So it might be hard for you to imagine a function that you can only differentiate once and no more, right? But they exist, right? So just because something is C1, you can't automatically assume, oh, I can just keep differentiating. You can't always keep differentiating. Okay? There are examples. So here's an example of a function you can only differentiate one time. So this guy lives in here, but he doesn't live in any of the other ones. But these are all vector spaces. Some more important examples.
So those are vector spaces, so that would be C over
R.
over R.
So
Okay.
they're continuous on R.
I see.
It'll also be continuous on C. They'll also work over C. With the usual arithmetic. These all apply to the usual arithmetic. So I'm drudging up now some examples you would have seen before that you might want to be starting thinking differently about. Here's something that some of you might have seen. Take a second order linear differential equation, or an nth order linear differential equation for that matter. The set of all solutions to that equation will form a vector space. Meaning if you have a bunch of answers, and we know that an arbitrary one will have an infinitely many number of answers, if you add two answers, you'll get an answer, right? And you can combine them in your answers to this equation in multiple different ways in accordance to the 10 axioms of a vector space, and they'll all work out. Here's another one. More linear algebra-y. The set of solutions to a homogeneous differential equation. Right? So i.e. if I look at the set of all x such that x is a solution to ax equals 0, if I look at that set with matrix addition and multiplication, it's a vector space. Quirky example for all the geeks out there. Magic squares. Does anyone know what a magic square is?
The number game, like.
It's kind of like a number game. It's kind of like a Sudoku thing that people like playing around, kind of like how people like playing around with prime numbers. These are n by n squares, but we can think of them as matrices. With each entry distinct. And of course the entries go from 1, 2, 3, all the way up to n squared, such that each row, column, and diagonal sum to the same number. Example. This is a 1 by 1 magic square. Right? It's called the trivial example, the trivial magic square. It turns out there are no 2 by 2 magic squares.
You meant 4 there, right?
4, where?
Where are these perfect squares? Or, what do you mean?
They're
by
squares, they're n by n matrices.
Oh, okay.
They're n rows, n columns.
Oh, okay.
There will be a total of n square elements. If you can populate this, not repeating any elements, such that every row, column, and diagonal add up to the same number, it's called a magic square. So it turns out there's a 1 by 1 magic square, there's only one. Turns out you can't create a 2 by 2 magic square. Right? You can't arrange the numbers 1, 2, 3, 4 in a square matrix such that the diagonals, the columns, and the rows all add up to the same number. There's a 3 by 3 magic square. And you can look at this using group theory, for example. Like 8, 1, 6, 3, 5, 7, 4, 9, 2. You notice that every row, column, this diagonal, and that diagonal, they all add up to 15. And I can say there's only one because you can prove that every other example you can possibly come up with is going to be some sort of reflection of this. Right? You'll either reflect over the diagonal, or flip this way, flip that way, but there'll really be, relationally, positionally, there's only one way to arrange these elements. Right? And then every answer to a 3 by 3 magic square is going to be some iteration of this guy. What do you think about 4 by 4? So there's one of this guy, there are no of that guys. There's one of this guy. You know how many 4 by 4s there are? Random. 880 4 by 4. You know how many 5 by 5s there are?
760.
You might as well. It's like, I don't remember the exact number. I wrote it down. There are more than 273 billion of them. You know how many 6 by 6 magic squares there are?
0.
No one knows. That is an open problem. We only know how many magic squares there are up to 5 by 5s. If you figure out a way to determine the number of magic squares that are above 6 by 6, there are estimates about this. It's roughly 1.8 times 10 to the 29 6 by 6, but no one knows for sure. That's just a guess. Right? Take 5,000 times that number is the number of atoms in the known universe. So there are a lot of them, right? And that's just a guesstimate. But no one actually knows beyond 5 by 5. We actually know the exact number here. No one knows beyond that. If you figure out a way to talk about the definite size of things that are 6 by 6 or higher magic squares, you will win a lot of money. You will be a millionaire if you can figure out that problem, right? The Mathematical Society will pay you millions of dollars for that proof, right? If you can prove it for everyone above 6 by 6, like here's a formula to figure out how many things.
But why isn't there a formula?
There isn't a formula. No one can figure it out. Look at how random these numbers were. One of these guys, 0 of that guy, 1 of that guy, 880, and it jumps to 273 billion. And when I say that, I mean they're distinct. They're not reflections of each other. Or you can, oh, it's just the same thing, but you just looked at it. No, they're completely different arrangements that have no connection to each other. Right? So if you take into account all reflections and flipping and symmetry,
It's a little bit more
you will
than
get more than that.
Okay.
Right? But these are distinct ones. Right? It's crazy. It starts to get crazy. And no one can figure out a formula for that. But it turns out that if you look at all magic squares of a certain size, you can prove that they fulfill all 10 vector space axioms. So they form a vector space with a set of n by n magic squares. So we don't know how many of them there are, but if you give me a bunch of 6x6 magic squares, I can prove that they have to fulfill the 10 vector space axiom. Of course, with scalar multiplication, you won't necessarily have integers anymore, but it will maintain, if you multiply all the numbers by a radical 2, for example, they will still all sum to the same number. It'll just be now an irrational number. We can go on and on and on. There are tons of examples of vector spaces. And we're going to talk about subspaces, and we'll see more examples there of some vector spaces. But these are just some common ones. So like continuous functions, differentiable functions form a vector space. So if you know that two functions are differentiable, when you add them you get something that's differentiable, and etc. So there are many examples that we've seen so far that you're familiar with that do form vector spaces, and some that don't. So that was a bit of a quirky example. Here's some more examples that we're actually going to be talking about soon. So let's look at, actually has a name, Pn. This is the set of polynomials of n degree or less. Over R with the usual arithmetic. We'll use this example a lot, and we'll prove things about it, and your homework will ask you about it. This set, the set of all polynomials of n, the degree n or less. Maybe I should write it that way. It seems more of degree n or less. Why do we need the or less?
Because adding two polynomials of that won't necessarily give you back that same degree.
Yeah, if I take two polynomials of degree 3, take two cubics, I can add them and get something that's not of degree 3. I can get something that's of a lesser degree. Right? So take a third degree polynomial and take its negative. Add them, I get a 0 degree polynomial. Right? So I need the degree n and everything below it. Right? I'll never get anything above it by combining them according to the vector space axioms. So the set of all polynomials that are of a certain degree or less, they form a vector space. Another common one that we will see sometimes is the trivial vector space, so it has a name. That's the set 0. This is, it's called the trivial vector space, or sometimes people call it the 0 vector space. It's easy to see that it'll work over any field, but let's just say it over R with the operation that take any two elements in this set, add them, you get 0. And k times 0 equals 0 for all k in R. So with these two operations, this set is a non-empty set that forms a vector space. It will satisfy the 10 things. By the way, here, this is an arbitrary definition. It turns out that is not obvious. In fact, let's actually prove that now. Here's a theorem. Let V be a vector space. I'm gonna prove some things that would seem obvious to you, but that's because you're thinking of things that in the real numbers. But they're not true in general. Well, I'm gonna show that they're true in general for vector spaces. Let U be an element of V, and K be a scalar. Then, here's some things. Be a vector space over R, or C. Then if I take the real number 0 times a vector, I will get the 0 vector. 2. If I take any scalar times the 0 vector, the result will be the 0 vector. 3. If I take -1 times a vector, it'll be the negative of the vector. By the way, even for real numbers, that was proven at some point, that multiplying something by -1 makes it the negative of a number. Of course, that was taken for granted. Another thing, if Ku equals 0, then the scalar K is the 0, or the U had to be a 0 vector. So if you multiply two things and you get a 0 vector, then this either has to be the 0 scalar or this has to be the 0 vector. There would be no other options. Which I know seems crazy, but they're... Why do we have to prove that? Isn't that obvious? It's not obvious. In fact, for those of you in my 308 class, when we're looking at congruence of integers, this is actually not true. And so if you look at A is equivalent to B mod n, and your n is not a prime number, it turns out you can have two things that are not 0 that when you multiply them, they become equivalent to 0, even though each individually is not 0. Anyway, let's actually prove this. Okay, what do we do? How do I get from that to the 0 vector?
Can you use the fact that a field, every element in your field has some kind of additive inverse? So let's choose like K plus its inverse. So you're rewriting 0 in another way?
Sure. I think your idea would help more with 3 though. But here's the trick. 0 is 0 plus 0. Right? Now that is by property of the real numbers. So that's not something I just made up. That's actually a thing that we would know. A field behaves that way. 0 is the 0 vector for the field R, and it is the number such that when you add it to any other real number, you get itself. So I can have this. Now what would I be able to say? I have a distributive property, right? One of the vector space axioms allows me to distribute scalars. So this means I have 0 times this plus 0 times that. And this is by axiom what? I forget the number, but it's by one of the axioms. Now what am I allowed to say? This means 0 times u is equal to 0u plus 0u.
0u is equal to the 0 vector because you added it to
This
something.
means 0u equals 0 by axiom 4. Right? Axiom 4 defined the 0 vector to be the guy that when you add him to someone, you get itself. Right? So this guy must be the 0 vector. I don't remember if we proved this, but if there's a 0 vector, it's unique. Right? We probably proved that. So this has the property that when I add it to this guy, I get himself. He's functioning as 0. It obeys axiom 4. So I can make this conclusion. If I take the 0 for my field, multiply by any vector in a vector space, I will get the 0 vector for that vector space. Now there are times in the past where I asked students to prove this, and what they did was so if I ask you to prove this in general, you write down something like this and say, oh, that's the 0 vector. What's the problem here?
You didn't specify what are that you was a vector like this.
Right, so what are, if you write this down, what are you assuming here? What are guys that look like this?
The components or scalars in your field?
Vectors in Rn.
This is Rn. Right?
It's just
So the moment you start a proof and you write this down, it means you're assuming the guys I'm talking about are in Rn. Notice that nowhere here said we were in Rn. V is any vector space. U is a vector in that vector space. It does not have to be an Rn. It could be a continuous function, it could be a solution to a differential equation, it could be a magic square that I'm talking about, it could be anything. It does not have to look this way. Which means that if the statement doesn't tell you that it looks a certain way, you cannot assume it looks that way. This is true in general, by axioms, not by, oh, it looks like this particular guy that I'm familiar with.
Professor,
Yeah.
could you just explain that part one more time? Like, from the second to the last line, and why it's true?
This, that?
Yeah.
Because there's an axiom that says there exists a 0 in V such that U plus 0 equals U for all U in V. Right? There's such an element. In other words, when I take an element plus this guy, I get this thing back.
But, wait, can I
Right?
just...
Can you see? Can you see?
No, so the line before the last one, right? Where is the 0 vector there?
I'm saying he's this guy.
You're allowed to claim that?
I'm saying this is 0. Yes, I'm allowed to claim that because 0 is defined in terms of what it does. The 0 vector is the guy that does this. When I add him to something, I get the thing itself. Right? So here's some guy. Here's some guy. When I add this thing, I get the guy himself. It made no difference.
Okay.
This guy, therefore, is an additive identity.
Okay.
It is something that I added to someone and it made no difference to the person. Right?
Okay.
So this guy satisfies that property. Therefore, I can call it 0. It's my 0. Right? And it doesn't have to look, you want to get away from familiarity in the sense that, oh, we're talking about Rn. It's not Rn. Right? A vector is any vector space, and I gave you a bunch of word examples because I wanted to drive that home. It doesn't have to be in terms of familiar things that you're thinking about. It's any non-empty set with a field, with 2 operations that obey 10 rules. They don't have to look a certain way. They don't have to be people that you recognize. They don't have to be familiar in any other way other than these properties of what they're doing. It's more important that what they do as opposed to what they look like.
Thank you.
So if I ask you to prove this, this would be incorrect. Right? If I said, if the vector space V is Rn, prove this is true, then this is fine. But if I never told you that, you cannot assume that. This would not be correct. So you'd have to be very general and not assume that this guy looks a particular way. Because you wouldn't be proving the claim. You'll be proving some subset of the claim. Okay, let's prove, so that was the proof for 1. What about 2? It's actually a similar trick.
could write it as k times the zero vector is equal to k plus 0 times the. Oh, no, that's true.
So we can do that. Why? Because we have a distributive property that says we can do that, and that's by some axiom, I don't remember the number. And now, again, this same principle. Here's some guy, I added this to it, and I got the guy himself. This means k times 0 equals 0 by axiom. Well, I think I remember that's axiom 4 because we use that a lot. Searching for 0 is something that we often do. If you have some set that you're not sure is a vector space, checking if it has a 0 vector is one of the first things people usually check for, so I'll remember that number of the axiom, but I don't remember the other.
So that one is vectors distribute over scalars, and that one is scalars distribute over vectors?
Yeah, and these are two different axioms.
Okay.
It's like axiom 8 and 9 or something. So that's true. What about the third claim? How would I figure out that minus 1 times something would give me the definition of its negative? What is the definition of the negative?
When you add it to the original, you get the 0 vector.
Right. So I need to show that if I add this guy to the original u, that the result is the 0 vector. That will be able to allow me to say that this is the negative of u. So how do you do that? So let's take u plus minus 1 times u. Now ultimately I want to say that this is 0. How would I be able to say that without taking anything for granted?
You distribute out the u.
I can factor out the u. There's an axiom that tells me that this will be 1 plus minus 1 times u. How do I know that u is u times 1?
Oh, property rule 10.
That's property 10, right? We're taking nothing for granted here, right? So even the fact that u times 1 will give me back the u is not something I took for granted. That's true by property 10.
Just a quick question for 2.
Yeah?
When you made use the distributive rule, I still understand why that was allowed. Like k times 0 vector plus 0 vector is equivalent.
Because 0 is equal to this by the definition of the 0 vector. If I add 0 to this, I get itself.
Okay.
That will work because this is the 0 vector.
Gotcha.
So I'm allowed to say this is equal to that. In fact, at any given time, I'm allowed to say that u is equal to 0 plus u, because by definition of 0, that's how it works. I can randomly say this at any given time. It's an axiom. So I just replace this by this plus the 0 vector, because that is that. And distributive law allows me to write this. The fact that I can add this to that guy and I get that guy means that this guy must be the 0 vector. Because that's the property of the 0 vector, and the 0 vector is unique. This I can expand. I know that I can distribute this and say 1 times u, and I would get back u because property 10. However, I do not know that minus 1 times u is the negative of u, so that I can't assume. But what is 1 plus minus 1?
0.
Well, that is 0 with the real numbers, right? And this, by the way, is 0. Why?
We proved it.
We proved it in part 1. So since u plus minus 1 times u equals 0, we have that minus 1 times u is the negative of u. Right? Remember, this guy was a notation. It represented the element that when I added to u, the 0 vector was the result. And I just proved that adding this thing, minus 1 times u, to u, gave me 0 as the result. 4. So we need to show if k times u is the zero vector, then either k is the zero real number, it's the guy that's in R or C, or u is the zero vector for my vector space, right? And that would look like something different depending on what vector space I'm in. Proof.
Didn't we do those? Like one and...
No.
If the first case, wouldn't that mean that it's like one of the other ones that you proved, and then the other one? No?
How would I say that in a proof though?
Could we do it by proof by contradiction?
Okay. What would that imply? Or what would such a proof start like?
K at times a vector u is equal to the zero vector,
Assume k times u is equal to 0,
and
but
but k is not equal to 0,
k is not equal to
And-
0, and
the u is not equal to the zero vector.
okay. Remember, so this is a statement, by the way, if this, then that. That's the statement. Remember, P implies Q. If you want to do contradiction, you have to remember that your assumption needs to be P and not Q, and you need to show that that implies a contradiction. Right? So you can't just tell me, oh, didn't we prove that already? You have to give me a structure, some logical structure that allows me to conclude the conclusion you want to make. So you decide to go with a proof by contradiction, meaning this needs to be the first step. Assume this is true, but that part is false. Right? If this is 0 or that is 0, the opposite of that is they're both not 0. Now what would that mean if they're both not 0?
And you can't get the zero. There's that.
Wait, doesn't that mean that there's no zero vector, which is a contradiction to the vector space?
Why? Why would that imply?
I don't know, if your k was arbitrarily chosen,
Yeah, k is something that's not 0, u is not the 0 vector.
Yeah, so you can't get the zero, but we assume that k times u is the zero.
So basically what you're telling me is that if I have a non-zero real number multiplied by a non-zero vector, then the answer has to be non-zero. It's kind of begging the question. That's what you want to prove. I'll give you a hint. We can't really, because the vector u is not something we really know about, it's an arbitrary thing. However, the scalars are things we know about. So let's focus on this guy, because if that's a real number that's not 0, I kind of know all its behaviors. What would I be able to say if k is not 0? What are some things that would jump to mind here?
You could say,
Yeah?
You could divide both sides.
We can divide by k. It is a property of real numbers that for any non-zero real number, I can divide by that. 1 over that number is also a real number. Since k is not equal to 0, 1 over k exists and is a scalar. So that's a meaningful quantity, and I can multiply it by both sides, or in other words, I can divide both sides by k. This would mean that k times u equals 0, this is by assumption, would imply that this guy is equal to 1 over k times 0, dividing both sides by k. Or you can think of it as multiplying both sides by 1 over k. But what does that mean?
that means that u is the zero vector.
Why does that mean u is 0?
Because of what we proved earlier, any constant k times the zero vector is equal to the zero vector.
Right, that was property 2?
Yes.
Yeah, by this. If I have any scalar times a 0 vector, then that thing must be 0. So here, I have a scalar times 0 vector, which means this thing must be 0. But that thing is equal to u. That means u must be 0. But we assumed u was not 0. So this is by part 2. But we assumed u was not 0, and so that's a contradiction. And that ends it.
So I'm gonna ask before I forget, because it's not clear to me. For 2, and going back to this, why is that? It's an axiom of what? Like
A vector space axiom. It's
Oh,
axiom,
oh, so
it's
because-
axiom 4.
Okay, I see. Wait, you mean as in because of axiom 4 of the original set of...
Of the original
Okay,
list
okay,
in
okay,
10,
okay.
if you look at number 4, it says that anything is equal to itself plus 0.
Okay.
So that would obviously apply to C
Right, right,
itself.
right. Makes sense.
Yeah. Right, so these are things that might seem obvious, but they weren't obvious, and we had to prove them at some point. And believe it or not, some of these things we had to prove for the real numbers at some point, but no one ever, they just never told you. Like, people take it for granted that -1 times a real number is the negative of the real number. That was something that was proven at some point. Someone proved that. But you know, they just told you, oh, 1 times anything, you can just ignore the 1. And why can you ignore the 1? Why? Why am I allowed to do that? I can't ignore any other number multiplying things. Why can I ignore 1 multiplying something? But I guess starting off preschool talking about multiplicative identities wasn't like, it wouldn't be, okay kids, let's talk about multiplicative identities today. An inverse that lives in a field. Okay. Like, I mean, you have these kids just struggling to count the marbles on, it wouldn't have worked out. So they had to just tell you something that, just believe me, this will work out. Okay. But things like that, we need to prove them for vector space because there are many things that would seem obvious that should work in the real number sense, but they won't work in the vector space sense. So it's important that we actually prove these things.
Are these proofs like observable in the same way that basic arithmetic proofs are?
What do you mean observable?
Like you can easily visualize on a number line, like when you sort of add 1 to -1, like what happens?
Oh, no. In general, the answer would be no.
Okay.
Yeah. And there are easy cases. You even look at something like R infinity over R. I mean, you can understand what that is as a concept, but actually observing that, an infinite, a tuple of infinite length, that's not something you can imagine.
That's like an infinite dimension or something, right?
Yeah, it will have infinite dimensions, which when we get to the section on dimensions, we'll talk about that. So there will be objects that live in this space that you can't visualize, that you can't write them down. But yeah, a lot of the things from the real numbers, the axioms, came from observable things. We're like, it just makes sense to us, right? To say that A times B plus C, there's such a thing as a distributive law. Where did that come from? I'll tell you where it came from. You have a square of length A plus B, square of length A plus B.
Shows on YouTube.
Right? Right, if this here is A, that length is B, and I cut this off, this length is A, and that length is B. Or, this is B plus C. This is B, and this is C. I was thinking of some other proof that I did earlier. And this whole length here is A, right? Then the area of the big square is A times B plus C, which is the left side. But you can also find the area by taking these two areas separately and adding them together. A times B plus A times C. So someone says, oh, this seems to be a part of physical reality. This isn't the fabric of nature. So they're like, axiom. We will assume this is true without proof. The real number will be a set such that this thing holds. Why? Because I'm a farmer and I want to be able to divide up my land and sell it in pieces and not be robbed and overtaxed.
How did they show
And so thousands of years ago, they're like, this has to be true because of commerce.
How did they show the negative version of that?
Well, negatives is
They were like
another.
vectors or something?
Oh yeah, remember like negatives and zero took like millennia to actually come into consciousness. Like, yeah, a lot of things had to come in. When we talk about negatives, we're talking about thousands of years after this fact was realized. So let's not jump. Let's not make that jump in like 2 minutes. Okay, so there are some axioms. There are things that we seem to us to be in the fabric of reality, and we can sort of capture this with real numbers, and so we can make axioms. But from that, you need to prove things. Like, it's not evidence in nature that -1 times some quantity is the negative of that quantity. What does that mean? Right? How can you see a picture of that? You can't. Right? That's just you extending what these properties mean to an abstract sense. Right? So like -1 times x equals -x is not something that's obvious in the sense that you can see it. And the things that we're proving aren't obvious in that way either. That's why we have to rely on proof in the way that we're doing. So I understand that it seems painstaking, but it's important that we be careful when we're treading brand new ground. Let's talk about subspaces. And by definition, we'll also talk a little bit more about vector spaces here. Kind of already been taking stabs at this, so I'll give you a definition. Let V be a vector space and this will be an abuse of notation. Sometime I'll just call a vector space by V without saying, oh, it's over this and these are the operations. But it should be understood that all that baggage comes with it. So if I say this set is a vector space, it should be assumed you're thinking of some operations and you're thinking of some field, but you're not telling me that's cool. I know they're there in the background. Okay? It's kind of like how when you're talking about sets, no one always identifies who the universal set is, but it's kind of, no, there's always some universal set in the background. You don't have to say it. So me saying there's a vector, V is a vector space is me saying there's some non-empty set. There's a field that comes have the scalars. There are two operations on this guy that worked out in these 10 ways. Okay. Let's look at a subset of V. We call U, which is a subset of V, a subspace. So I'm defining the word subspace. If and only if U is itself a vector space. With respect to the same field and operations as V. So this is talking about when I have one large group of things that I know is a vector space. I've already verified the rules for them, but I don't want to look at the whole thing at once. I want to talk about a little subset of that thing. And I want to know, can I apply my vector space rule to this subset I made, right? If I can apply all the vector space rules to that set is called a subspace. So it's a smaller piece of a much larger vector space that might be important for us to study for some reason, okay? And so V can be a vector space, but I'm looking at some subset of that V, and I want to know, is that subset a vector space? In the event that it is, I call it a subspace. Here's a nice thing about subspaces. You can get away with verifying two axioms. Let U be a subset of a vector space V. Then U is a subspace if and only if there are two things you can check. Do we know the two things?
Closure under addition.
One is closure under addition. That means if I take x and y are in U, then x plus y is in U. When I add two things in that subset, the result is also in that subset. The second thing is closure under scalar multiplication. That means if x and y are in U and k is a member of your field, then, well, I only needed x, then k times x is a member of the set. So we looked at this. For example, I can look at the set of all possible 2x2 matrices over R, right? All possible matrices where the entries are real numbers that are of size 2x2. Then I can look at a subset of these guys. Let's only look at the guys that are invertible, right? Do they form a subspace? The answer is no. Why? This rule fails. Well, both rules actually fail, right? If I add two invertible matrices, I don't get an invertible matrix. So I can add two elements that have the property I care about, but their sum don't have the property I care about. So by adding them, I exit the set, right? So the answer to the arithmetic I want to do within the set gives me an answer that's not in the set. And that's bad, right? So it's not closed under addition or scalar multiplication, right? So that's how we verified, for example, that the invertible matrices do not form a vector space themselves, so they definitely aren't a subspace. Because being a subspace means you're a vector space in your own right. You're just a smaller part of the universe, but you also have all the property. You're a microcosm of the universe. Okay. Proof. Assume U is a vector space. Then, what direction am I improving here? So I'm improving in this direction, right? The forward direction. If it is a subspace, then these two things must hold. Then I want to prove that if these two things hold, then it will be a vector space. Then the 10 vector space axiom holds. And they include these two properties, so I get them for free. Let's go the backwards. This one is slightly more challenging. So here's one proof that assume 1 and 2 hold for U. Since 2 holds, zero times U is equal to the zero vector for U in U. So U contains 0 for V. This gives axiom 4. So it means U contains a zero vector. It contains an element that has the property of the zero vector, and it turns out it's exactly the zero vector from its parent set. How do I know? It's closed under scalar multiplication. We've proven that the zero scalar times a vector is the zero vector. So because u is an element of the set, 0 times u must also be an element of the set, but 0 times u is 0. So our subset contains the zero vector. And by the way, this is by the theorem. So I know this is in U by assumption, and this is equal to the zero vector by the previous theorem. So U contains the zero vector. So that's axiom 4 will be satisfied for U. Also, if I take the scalar minus 1 times U, I will get the negative U. So U also contains all its negatives. What axiom dealt with negatives? I forget. Anyone remember where I wrote it down? That was axiom 5. Axiom 5 holds. 1 and 2 are axioms. What's the number that I gave them in the list? Closure under addition was axiom 1, was it? I believe that was axiom 1.
Yeah.
Our axioms 1 and closure under scale multiplication was axiom 6.
Yes.
Our axioms 1 and 6 respectively. So remember, to prove this is a vector space, I have to prove it satisfies 10 things. So far, how many things do I know get satisfied? Axiom 4, axiom 5, axiom 1, and axiom 6. That's 1, 2, 3, 4 things we verified so far.
Actually, I still want that axiom. I mean, I'm looking through the properties. I don't see that. I mean,
Oh, no, this isn't a property. This is a theorem.
Oh, okay.
The previous theorem proved that minus 1 times u was negative of u.
Oh, okay, I see.
Because all the scalars multiples are in u by this property.
Okay.
It means this guy must be in u, but that guy is this guy.
Okay.
So every element contains a negative that is also in the subset. And it turns out the other 6 properties you get for free, because every element of U is an element of V, so the behavior of elements of V by themselves, the U guys will obey them as well. So you notice that the other rules, they don't deal with the existence of some guy that we don't know about yet. Oh, there must be a zero vector out there, let's go search for him. The other rules are just about, this is how this thing behaves, right? They will be commutativity, for example. I know that things in U must commute because they're elements of V, and the elements of V commute. So I get that for free. I don't really have to prove that because they are the elements of V. So since all elements of U are elements of V. Since all elements of U are elements of V. So it turns out to prove something is a subspace, I only need to verify 2 axioms. I need to verify that it's closed under addition, well I erased them, it's closed under addition and scalar multiplication. Okay. So this allows me to save a lot of work. If I already took the time to verify all 10 things for some larger set, then if I look within that larger set at some smaller set, I only need to verify 2 things to know that that smaller set is a subspace. So if I want to say, I know the set of all 2 by 2 matrices is a vector space, what about all 2 by 2 symmetric matrices? Now when I look at the symmetric matrices, I only need to check 2 things because I already verified the 10 things for all 2 by 2 matrices. You understand? So it cuts down, this theorem helps us cut down on work. And that's probably going to be the next example I do, so you guys can try that and see for tomorrow. Could you prove, I'm going to do that as the first example. Use a subset of M to 2. This is the set of 2 by 2 matrices. Where U is the set of all symmetric 2 by 2 matrices. Show U is a subspace. It turns out to do that, you only need to check 2 things. You need to check that when I add 2 symmetric matrices, I get a symmetric matrix. And if I multiply a symmetric matrix by a scalar, I can get a symmetric matrix. And that will prove that it's a subspace. So we'll do that and more examples next time, as well as start getting into some neat stuff. We're going to look at the underbellies of a lot of the things that we've studied that we think we're familiar with, but we're going to realize certain things connected that we probably never realized before. And ultimately where we want to bring this all back to functions. And so we're going to prove a bunch of things for matrices. They're going to be our principal vector space and the tools that we're going to use. And so we can ultimately think of these guys as functions, and so the functions will behave as elements of a vector space, which allows us to talk about a lot of other things. So we'll stop there. I'll see you guys tomorrow. I already posted the review for test 1, so be sure that you look over that and start practicing.